T.N. Professor T.N. Krishnamurti from the Florida State University and Professor D.R. Sikka. He was the former director of IITM Pune. What distinguishes them is that they have more than 50 years of working experience in this area.
It's more like a plain, and the island of the city of Lihu is sort of the principal city in this island. There are rivers that come out of here. There are some rivers that go here also, and also there are rivers here. One of the well-known things about this spot is that one of the biggest annual rainfall places in the world. I'll be talking a lot about those. 80% to 85% of the days, it's undisturbed weather. And yet the rainfall amounts will go to somewhere near 430 inches per year. And most of that rainfall comes from undisturbed Stratocumulus and towering cumulus invading this mountain here. And these mountains are not very deep. I'll tell you all about them. They're not very deep.
Can I just ask a question? Undisturbed means no synoptic scale system?
Very good. Undisturbed means no typhoons, no hurricanes, no synoptic scale, no middle latitude disturbances. Those come very infrequently. And so, anyway, keep going. There are many places on Earth where they have this kind of thing. Heavy rainfall in excess of 448 inches per year listed in them. Colombia is by far the leader. I have brought some pictures on what exactly that place looks like. Again, invaded by this army, but not Mayaswaram and Cherrapunji. What happened here was Cherrapunji was number one. Suddenly, it found itself to be number 4 now. And what happened was in Hawaii, they had the rain gauge for the longest time just northwest of Lihu, that city I pointed out. And then they found that when they look up, the rain was falling a little bit farther away, and they decided to move the rain gauge there. And they find that there is a spot. Please remember this. There is a spot about 2.5 miles square where it just keeps on raining. And so they put the rain gauge there, and when the Indians found out, they said that they can find another place. And so ever since then, they have different rain gauges. So anyway, this is what it looks like. I'm looking, unfortunately, we are looking at, we're looking at from the north, we are looking at the Mount Waileale. This word comes over and over. That's the mountain in Hawaii. And so if you watch some of these things, they will rise up as they come here and produce rain here, and they go on up. And then, anyway, this is sort of the panorama of shallow stratocumulus invasion that goes on all the time. That's what it looks like from a geostationary satellite. This is one of the GOES West satellites at 4-kilometer resolution. So what you see here is this army of stratocumulus coming in. This is some upper level disturbance in the tropics, and that's another westerlies with some disturbance farther out west. But in between, you have this invasion into the Hawaiian Islands of these things, of which several of them are passing through the northern island. This is what we are talking about. And they end up producing about 350 inches of rain per year in Hawaii. And so we need to understand them. And actually, I think the potential of this scientific problem is so big that you can do all kinds of things with it. That's what I found, I have to say, on a Google. So it said a satellite picture on the same island and those two arms. And this is how the clouds seem to look like when they're invading this armchair. They call it an armchair like that. And the clouds come in, rise, and just keep on raining, and almost average of inch a day on undisturbed days. This is what the trades look like. This is a flow at 1.5 kilometer above the ocean, the so-called 850 millibar. And you can see the island there, and the trades are pretty much coming from the northeast trades over and over and over there. There are few days for sure. Anywhere there will be some fluctuations and disturbances passing by. But by and large, this is the kind of flow. What kind of wind speeds? The wind speeds are about 10 knots. 10 knots, and I'm sorry, am I saying this? Yeah, it's about 10 knots. And that is sufficient to have this orographic ascent of very moist marine layer that is bringing in this army and producing this kind of rain. The height of the mountain is around 1.5 kilometers, so same as the flow is pretty nearly the same all the way down to the surface, except the surface flow has slightly more of a northerly direction because of the frictional. This is what the radar looks like at Honolulu. The Honolulu radar is located here. I'm sorry, I'm saying it wrong. Yes, it's located here, and unfortunately I couldn't get too many radars, but what you see is occasionally you can see these mergers, and so this is on a better scale than the satellite. Satellite, when I say 4 kilometers here, you're seeing like 500 to even 400 meters, you're seeing some returns in the radar signal. And the radar shows the same army just day after day going by, and as innocuous as it might seem, this is one of the world's record rain producer. So this is more of the same for different days. And so basically, in a very simplified manner, the trade winds are undergoing orographic lift. The lifting condensation level is close to the base of the cloud, and the top of the cloud is close to the base of the trade wind inversion. There will be some penetration, and so you have basically the cloud here and rising this way. These can be numerically modeled because the basic flow is large-scale flow. Remember that. It's not mesoscale, it's not hurricane scale, it doesn't have all kinds of small scales. It's very large scale, invasive flow, just rising over the mountain. So you can predict these with the existing models, provided you have the right kind of microphysics, and meaning the rain rates. So I'll be showing you, I'm skipping this. There are conditions under which the flow would occur around the mountain or over the mountain, and those depend on a non-dimensional parameter, which is h over nl or something. Anyway, the Brent-Weisser frequency and the height of the mountain and things like that get in. And we find that in the Hawaiian region, the flow is such that flow over the mountain is satisfied by those. I'm not going to go into this right now. So this is what the tipping bucket rain gauge was. The special rain gauge that they deployed at Mount Wild Elias, that's 2.5 miles square. In the middle of it, they threw it in. And what it does is it tips every single day, and so it makes a fresh recording every day. So you can get the daily returns, and all of this is transmitted to Leahu, and from there this data is collected, and they have the data for going back to about 6 years. 2007 they started this. And so I think it's useful stuff, and this is the kind of thing that can be deployed in many places for reasons I shall tell you later. That's what the data record looks like. From this rain gauge, this tipping bucket rain gauge, in 41 inches in April, 18, this was a particular year, 2010. So we're talking about getting up to numbers like 420 inches per year. This is just a small sample of six of those months in 2010. And even if you looked at the average of these 6 months, it's around 26 or so inches per month. And it rains all the time. Please keep that in mind because that's important. And one of the simplest way, I'm going to exploit this particular notion with some modeling, which is in any cloud resolving model, if you leave out the immediate effects of accretion or coalescence and simply ask the disposition of supersaturation, then this is the measure of the disposition of supersaturation rain. And if you are doing that in the immediate vicinity of a mountain, then the orographic ascent can be the advection of the flow and the sloping terrain dH/dx. And so you can combine these, and there is a triple product in here. This triple product is very important because of various issues. Among those, what part of the mountain, for instance, is most active in producing the rain. What happens is these are such shallow clouds. We're talking about clouds whose base is around 600 meters above the ocean, and the tops are about 1.6 or 1.8 kilometers. And they are coming by, and like a sponge, they give you the rain. It's called the warm clouds. And there's a lot of them. So the gradient of the terrain is very interesting. This is at the top of the mountain, and dH/dx is negative all the way through as you go east, and that slope is important. And there are very few places you have the right kind of slope to talk to shallow stratocumulus. Many places they don't meet, and so anyway, I can't go into all of that. This is the vertical derivative of the saturation-specific humidity, which is a player in the disposition of supersaturation, and that's what it roughly looks like with 0 below the LCL. So the wind is all negative, and this is the wind, a wind that was used for the computations, and the triple product looks like this, with the maximum reaching around 0.8 or just about 0.8 kilometers above the ocean. And the LCL is around 0.6. I'll show you that in a minute. If you take the Wailili Hill and do a backward trajectory over the ocean, Pacific Ocean, going to the east, and you can ask the question, you are interested in various things such as the relative humidity, how moist is it? And you do see a marine layer below the inversion, so to speak, with relative humidities in excess of 80-90% all the time. They're just coming in, very rich in moisture, not exploited for any purposes other than these mountains which have produced this enormous rains, because that's all in here. Now I'm going to show you the animation of static stability. The dry static stability gives you the base of the inversion below this red one, and below that the stability, the clouds are growing, and the cloud tops barely reach the base of the inversion. So that kind of dictates the shallow. Look at 850, 1.5 kilometers, and it's clouds are all within that. So if their cloud base is around somewhere here, and cloud top is here, and a rich amount of shallow.
Is it a boundary layer there? And it's almost at the edge of the boundary layer.
Yeah, quite close to, yeah. It's not 100% anywhere. It's around 90%, yeah. This is what the cloud base looks like. Unfortunately, it's at sites obtained from a reanalysis, which does use the Lee-Hugh data. And so this is the Wailili the mountain is here, and there are 6 grid points around it, and no matter where you look, they all seem very similar around the mountain, because Pacific is on this side, Pacific is on this side, and so the influence of Pacific is such that you have it around 600 meters, and over here it seems to have gone down to 400 meters for a time. So like what you said, the base is quite low. Okay, to keep that in mind. So what's happening? You have a mountain which is 1.5 kilometer high. This air comes and forms a cloud already at around 600 meters and rises, and there is a very strong possibility of this triple product being maximum just around 800 meters. So you can get a huge amount of rain from the disposition of supersaturation as the orographic uplift occurs. Now going on to a WRF perspective, there are triply nested model, but it's 500 meters is what I've used on the interior all over. And then I have 1.5 kilometers, 0.5 kilometers, and then 4.5 kilometers. And so it has a whole lot of things, but for the perspective of this problem, the Goddard Microphysics turned out to be the most important. And so I did bring some slides. I don't have time, but I'll say a few things about Goddard Microphysics. For this kind of rain, which you see from shallow stratocumulus doing world records, it seems to work very well. Okay, going back to historically, non-precipitating stratocumulus modeling.
I hate to interrupt you. Sorry about this.
Yeah.
You refer to those clouds as stratocumulus.
Yeah.
Cumuli. These are not stratocumulus.
They are stratocumulus in the sense that eastern Pacific, the stratus forms, here is the panorama. Stratus forms off the coast of California all the way, and then it comes out as stratocumulus, then the cumulus starts. After that, to go to the ITCZ.
And then it transitions.
No, you know, okay. Yeah. No, I think we have to move on. Sorry, I have a lot to say, so I'll come back to you at the end. We'll sit with you. Okay, Murray and Anderson wrote the first paper on non-precipitating shallow. This was right after Malkus and Witt, buoyant convection, the first paper. Anyway, basically what they had was a stream function with a buoyancy term, and you might call it a friction term. And then they had, of course, definition of the stream function, a first law of thermodynamics. So these two were coupled. There was processes where water vapor and liquid water would talk to each other, but the water substance will be nearly conserved except for the dissipation or diffusion processes. And so during the exchange between vapor stage and liquid stage, there will be either cooling or warming. Those phase changes were affecting the temperature. And so this model produced an elegant, I'm just skipping, so you take a conditionally unstable X is Z cross-section, minimum theta E here, below that the theta E is increasing downward and increasing upward, and you perturb it with a buoyancy, and that one buoyant element goes into this shape, and then finally forms this plume. Above the axis, x equal to 0, there is symmetry, so you can think of it as a double-shaped mushroom. Right, comes out like that. In 20 minutes, such a growth occurs, and it's entirely non-precipitating and that's the way most of them are. When these are coming in the ocean, the stratocumuli, they don't rain. So this is what the vertical velocity at the x equal to 0 axis looks like in the first 20 minutes and thereafter. The vertical velocity increases with time, and the buoyancy produces a maximum vertical velocity here of something quite large, about 20 meters per second, and then the cloud is here essentially dissipating. So this happens in the first 16 to 20 minutes, and the temperature field is fascinating. The temperature field carries a warm core, and then it has a cold core aloft. This is the penetration cold core into the stable layer aloft. Murray told me an interesting story. I have 1,000 stories, but I cannot tell. He flew an aircraft to measure these temperatures, and he said his aircraft destroyed the temperatures. It just because it was going through such a small cloud, and you're talking about very small scale, and so he could not measure those temperatures. The Goddard Microphysics is the next generation where you have precipitation as they are forming towering cumulus and cumulus. I don't want to again say too much. This is inside the WRF nowadays. Before they had other microphysics, they have added the Goddard Microphysics. The Goddard Microphysics contains equations for cloud water, rainwater, snow, grapple, ice, and so forth. And among the terms, they have local change and convergence and divergence of fluxes. And they have source and sink terms, and they have transfer terms. These transfer terms are important. And then there's this diffusion or dissipation. These are the transfer terms that communicate between those various species, each other, and in the process, of course, the thermal equation will also come into the picture. Symbols, more symbols. This is the diagram that the Goddard Microphysics Venn diagram, which is rather well known, used, but fortunately, this whole part of the diagram is never used for shallow stratocumulus because you don't have cloud ice, you don't have snow, you don't have grapple. So this is not going on. Just this little red part is going on, which is kind of summarized on the next slide, which I borrowed from a friend of mine. It has water vapor, condensation, evaporation, cloud droplets, collision, coalescence, accretion, and raindrops. And the sedimentation is not there, not here, but other places where there are stratocumulus, sedimentation can be there because you have high-level things going on with them. Anyway, and these are all the processes, autoconversion, accretion. These are all fascinating, and everything is sensitive to whatever you do in these things. The results are quite sensitive, and you have to look at them. Evaporation. Anyway, so having done this, what did we do? We said this is a large-scale problem in the sense the flow is large-scale. There are no mesoscales here. And it's coming and invading a mountain, so you have to simulate these with such a model. Model has to simulate the army. It has to produce the stratocumulus. You have to get some kind of reasonable population of towering cumulus. 17% is that number. It's roughly that. The third thing, you want to simulate the climatology of the Vialia rain, the rain gauge. If you get those three right, you have a good model. I haven't gone quite that far. I've gone quite a ways that far. This is the simulation of day-by-day rain for one entire month. Half a kilometer resolution. That's the rain gauge, and this is a grid point very close to that rain gauge. And this is a large-scale problem, so don't think that because it's raining heavily, we are dealing with a mesoscale problem. It's not a mesoscale problem. And you can replicate these one-day forecasts. The ending date is the end of the forecast. So you take the one-day rainfall, and you can see that it's possible to. And a lot of this rain is undisturbed trade winds that are producing this. These are daily maps of these. I didn't bring all of them, but by and large, you can see the location at very similar location the heavy rains are falling. So that, and these are two examples in April when this episode was rather intense, but again undisturbed. And so you were getting like 2 inches of rain, not inch to inch and a half of rain. You can model it. Provided you have to, okay, I have to say this, you have to tune the Goddard Microphysics. And so that you get the result, you do get the rain, but to get the right numbers, you have to tune it a bit, which we have to do. It's a long story, but why do you have to tune it? Now I'm going to say, you have to tune it because of the southeast coast of India. What the hell has this got to do with that? Okay, so we're coming to that in a minute. This is what the radar looks like. Liquid water mixing ratio. We're in the model. And this is the vertically integrated liquid water mixing ratio. And the army is there in the model. And you can see it for days on. The army is always there. The model simulates the army, but is it a good army, and I have to answer that question. The satellite sees army with its own resolution. Radar sees the army with its own resolution. Model sees it with a third resolution. They cannot all be the same. And so you have to keep that in mind. I mean, there's no way getting out of it. Okay. Move on. This is the cloud resolving models, radar reflectivity. So when you have all the hygrometeors in the model, inversely you can compute what the radar reflectivity implied by the model is. And that's this. So you see, again, basically what you see is the army coming in of the stratocumuli in the model and going by the islands. I mean, it just tells you the nature of the numerical beast. Liquid-water mixing ratio, they come by cloud, and there's a bunch of them here, and they really show up nicely on this side of the mountain. They rise over, and then you can see this again, coming over, and then you'll see that it explodes a little bit along the slope, and then comes over. What happens, I'll show you next, liquid water mixing. There's also a film of this kind for buoyancy. I think maybe I didn't bring it. Okay, no, it is here. This is a film of the same thing for the buoyancy. The buoyancy is very interesting. Buoyancy is the difference between a property inside the cloud versus immediately outside the cloud. That can be computed, and you can make, and that's what you are seeing. So cloud by cloud you are seeing these, and when that cluster comes, you see let's see it once more. Yeah, as it arrives, there's a lot of buoyancy over the mountain, and then it rises over. What happens is, like anything else you can advect. I saw, in fact, in detail, the buoyancy itself gets advected, and the clouds go wide. The winds advect almost anything. And I need a glass of water, so sorry. Thank you. Okay, I'm going to skip this, but just say I'm moving on to northeast monsoon. Why am I moving on there? Because I looked at this army all over the world, and I have maps of these to show you where all you find the Stratocumulus army marching by with a wind stream like the northeast trades. And the northeast monsoon for 4.5 months carries many days of undisturbed similar feature. And so here is a typical high-resolution polar orbiter satellite image at 4 kilometers. And you can just see here the Stratocumulus. And this is India. And it turns out that northeast India likes this part. So it comes here a lot, all these flows. And there is a lot of undisturbed days. We found that there were close to 73% of the days in the 4 months that are undisturbed look like this. And there are eastern Ghats here. But not hardly any rain on undisturbed days in the eastern Ghats. Why so? Many reasons, but very quickly saying slopes are not favorable for the covariance, for the triple product. What happens is the slope and the cloud base and the vertical gradients of saturation, specific humidity in that vicinity, they don't give you the maximum at a reasonable level. So anyway, let me zoom it because it's asking for it. How do you zoom it? Oh boy. It doesn't. Oh yeah, it came. Okay, that's the zoom of it. So you can see that it's not unlike that in the Pacific Ocean. When you fly sometimes from Chennai to Calcutta or something, you might see some, but very often we don't look for these things, but they are there. I mean, cloud motion vectors that the Indian Met Department produces, they produce a lot of cloud motion vectors. That's shallow stratocumulus moving. Sorry. And this mean for December and mean for January and mean for February. Along here, you have the northeast monsoon doing something similar but at a greater angle than the northeast trades. And so that's the mean map for January. And now I looked around for mountains. In the Eastern Ghats. And I found that there was various reasons. As I was looking, somebody mentioned that Karnataka and Tamil Nadu fight for water. So I said, maybe this is a perspective for water for Chennai. So anyway, the mountain, the dimensions of this mountain are not unlike the dimensions of the other mountain, both the width and the height. Not very tall, and it has the 10 to 12 mile width. So that basically what I did was the following. I did a series of numerical experiments with this mountain and the Northeast Trades. Same model, same resolution, same everything. Just simply dump it. All physics the same. And the flow field is different. And I did first with this mountain. I got no rain on undisturbed days. As you shouldn't, and the observations verified that. Then I ported the Vyalilia mountain to Kolur. I just brought it, and I removed this first time, and I just plunked it on top, and asked the question if there was, and I started getting 1 inch of rain on undisturbed days, or less than an inch to up to 1 inch. I have a lot of data here, but I didn't like that. And then by that time, people in Chennai and I were communicating. So they said, this is an engineering enterprise, possibly. So you have to only put the front face of the Wadu Hills be replaced by the front face and the armchair of the Vyalilia. So that's what but then I turned the thing around. You have to turn it because you want the winds to hit perpendicular. You don't even want it east-west or slightly east-west as it was in Hawaii. So I turned it around, and lo and behold, every single undisturbed day, I could get 1 to 2 inches of rain. And so I quickly go through this. This is the flow field of the northeast monsoon. This shows typical 82 days out of 124 were undisturbed. And these are in different, somewhere between 80 and 90 days are undisturbed, meaning northeast monsoon is just coming there and not raining. Although it has a boundary layer not unlike that, very moist, 90%. You see these things coming in, very shallow many times, very similar. And near the mountain it's a bit deeper, but the mountain is right here at this end. And they're coming from east. And this is for a couple of months of data that I kind of displayed for you, so you can quickly see that it's very similar to Hawaii. The air is very dry aloft, so it doesn't permit deep convection. It's all shallow convection that's doing that carries a potential for very heavy rains. And this is the dry static stability of that region. And the base of the inversion is here. Base of the inversion is below the red. And so the clouds can penetrate up to that level, up to here. And so the fluctuations are a little bit larger, clearly, because there are some disturbed days in here, and there are undisturbed days in here too, because this is the entire month. So if you typically look at this day, for instance, the last day here, 15th of February, what you're seeing is you'll have very shallow clouds just penetrating up to here, so not very active clouds. But over here near the mountains, they will start going up. Okay, now some interesting differences. In this mountain, the Wadu Hill, Tamil Nadu, to the west side of it versus east side of it, the lifting condensation level is quite different. In the front of it, the lifting condensation level is 500 to 600, just like Hawaii. It's almost the same like Hawaii. Back here, because of possibly the ascent and descent of air, dryness here, so the LCL goes up in these grid points 1, 2, and 3. Those are the first 3 curves. And this is Hawaii, what you saw previously. Hawaii has a mean of 600 and 400, and you can get that in that region. And you have moist air. There's a lot about the handling of the terrain, so I cannot go into it's awfully fascinating, because you have to do a lot of trigonometric x prime equal to x cosine theta plus y sine theta, and y prime equal to x cosine theta minus, and you rotate, and then you have to do an objective analysis to get back to the old grid, and so forth. And anyway, this is the Hawaiian mountain on the Javadu Hills, just placed on it. And this, I'll show you in a few minutes. This is what the Eastern Ghats looks like, and then this is what it looks like after the thing has been put in. This is fascinating. The triple product is such, after the mountain has been put in, which gives the right slope, you get a maximum possibility of producing rain here, which you did not have previously. Previously, when you had just the good old Javadu Hill, that was this curve, and this is what you are able to magnify within reach, meaning these mountains can be built because front face can be built. I'll tell you a few things about those. I'm going to there past time. The daily rainfall, fortunately, very small area where it keeps raining in the same place all the time, very nearby. Again, it's around about 4 degrees square area where it's raining all the time. I put the arrows on these, and they're almost in the same place. And so, and what of these rainfalls look like? These are the rains produced on days when there were no rains whatsoever. There were no rains observed, but after the hill was placed and rotated, you had between 1 inch to almost 1.5 inches for every one of these episodes. Some were close to 3/4 of an inch. On the average, it was possible to get 1 inch of rain almost every day. Anyway, and this big difference that I found was in the slope, and the critical region where the slope is most important is between the LCL and the, I'll come to that. Yeah, there are two, okay. Now going to a bit of geoengineering, talking to people. If you do the rain harvesting down here, and you can collect as much as 400, we came to a number on the average 411 million liters of water per day. And if you are able to transfer most of those to a place called Fundi Lake, good distance away through a pipe, then there's a very interesting thing that happens. This is all downhill, first of all. Between Javadu Hill and Fundi Hill, the height here, elevation, is around 800 meters, and down here, the top of this 900 meters, and then here it's barely 100 or 200 meters. So if you lay a pipe, you're laying the pipe go downhill all the way. But this is done at a resolution of 500 meters. If I go to the length of the pipe resolution, say 3 meters or so, then at that resolution you may have to see finer topography and have to worry about digging. But anyway, this is what the Chennai water supply looks like. Chennai receives most of its water from 4 major reservoirs. Fortunately, these 3 are connected to this one. So we don't have to connect any pipes to these. In principle, all you do is connect the Javadu Hills to Fundi Lake, and it immediately connects to Red Hills, and Red Hills connects to both of these and connects to the Chennai City. Chennai City has a population of, these are the 4 reservoirs. Chennai City has a population of 15 million. And how many dollars do they have to each give? Turns out that $12 a piece will do it. It comes to $170 million to build the critical wall between the most important levels, and other places we can build a wall which doesn't have to be that sensitive. Well, it's not that sensitive. And so it's possible to supply this many cubic liters of water. This is what they need per day. I'm sorry, this is what they need per day. Oh, I'm sorry, I'm saying it wrong. This is what they need per day, and that's what they have at the present moment. They have a shortage. This is something in the future. It can go a long ways. It's better than desalination, because I saw the numbers on desalination. That's around 200, and it's not even complete at this point. Going on, these are other places in the world. where this can be done. So many places I've looked at. And the summary is what I have told you, namely, you start with Hawaii, and you can project that information. And one of the interesting aspects is that triple product. And the triple product is largest between about 800 meters and a kilometer. So in that region, you have to have the right slope. And even below that, you need the right slope. But about that region is critical for cloud interaction with the mountain. Thank you. Yeah. Yeah.
Okay, let's leave alone the Stratocumulus versus Cumulus.
Okay.
But couple points. First of all, you probably are aware that in the 80s,
Yeah.
there were big projects in Hawaii that specifically look at the rain formation. One was Joint Hawaiian Warm Rain Project.
I've read all those papers. Yes.
Yes. So anyway, you didn't mention anything of those,
No.
so I just wanted to.
No, I read all those papers. You will be surprised that they did not address anywhere the heavy rainfall issue. Why it was special?
Well, because I think
No, meaning the thermodynamics and the moist
the
thermodynamics of that.
emphasis was then, if I remember correctly, on the interaction between flow dynamics and the.
No,
and
no,
the
they
mountains.
talked about it. They talked about it. You're talking about the paper by Ramage and someone. Yeah, I have the paper with me in my computer. In fact.
All right. Now, but the other point, which I think is actually quite important, is that there is a big microphysical difference between those clouds that march over Hawaii, which are very pristine environment. The air went thousands of kilometers over pristine air, and it's very clean.
Yeah, surely.
And they precipitate very easily, whereas those clouds over on the southern India, I would imagine, are not as clean.
No, it's a good point.
And the
It's a good point.
the microphysics that
what
we
you are
use
saying
don't
is
have,
what you are
don't
saying.
have hookups for those
Yeah.
things.
No, what you're saying is aerosol with microphysics is important, possibly. Yeah. No, I don't have that in there. That's correct. Yeah. Yeah.
The rocks in Hawaii erode in a peculiar way, the volcanic rocks.
Yeah.
And presumably there's a very strong coupling between the precipitation, the resulting erosion, and hence the
No, the
evolution.
erosion occurred before the world record ever came. The erosion was volcanic erosion, meaning the fire went up, ashes came, and then smashed the whole. In other words, the mountain killed its own half. Yeah, as it came up.
The question I was driving at was, to what extent do you think the Hawaiian situation is influenced by the water erosion from the clouds? And
Yeah, that's a good point.
Is there a feedback mechanism that could, for example, optimize this?
Yeah, I was reading on the history of the Eastern Ghats, going back to way back to millions of years, and what I read there was in the early formation of the Eastern Ghats, they were as tall as 3 kilometers, which means they were more like the Western Ghats. And I don't know where Western Ghats were then, but 3 kilometers, and they eroded down to 1.5 because of the heavy rains, and then became a less rainy place.
Well, for your simulations around the Javadu Hills, if I understood you correctly, you change the wind direction.
No, I don't touch the wind.
No. When you put in the Hawaiian thing.
Hawaii, no, I don't touch the wind direction anywhere.
Okay.
Wind has to come as they come.
Okay.
In Hawaii, nothing is changed. Hawaii mountains
Hawaii
as
is
they are.
changed.
But
when you
in
did the
South
simulation-
India, I did insert a front face of the
Against the wind.
and then filled it up with concrete, so to speak, and then it was the Eastern Ghats behind that. It was just 2 grid points of the front face. Because you have
So what was the most important orographic parameter there that had to be reproduced?
the horizontal gradient. Yeah, that particularly, I think both below, but more so just above the cloud base and to the top of the cloud. That's where it's most important.
Okay, thank you very much, Professor Krishnamurti. Very fascinating.
Sorry, it took too long, isn't it?